Welcome to section 4.4, logarithmic functions. All right, so let's recall that an exponential function y equals f of x is 1 to 1. Okay, so it has an inverse function defined implicitly by the equation y equals f of x equals a to the power x, where a is greater than 0 and a does not equal 1. This inverse function is called a logarithmic function. Let's define now the logarithmic function with base a. The logarithmic function to the base a, where a is greater than 0 and a does not equal 1, is denoted by y is the logarithm with base a of x, and is defined by y equals the log base a of x if and only if x equals a to the power y. The domain of the logarithmic function y equals log base a of x is x is greater than 0. So as this definition illustrates, a logarithm is a name for a certain exponent. Okay. All right. So when evaluating log base a of x, think raising a to what power will result in x. So in our first set of examples, we're going to be relating logarithms to exponents. So if y equals log base 7 of x, then x equals 7 to the power y. For example, 2 equals log base 7 of 49 is equivalent to 49 equals 7 squared. Okay. If y equals log base 4 of x, then x equals 4 to the power y. For example, let's say -1 equals log base 3 of 1/3 is equivalent to 1/3 equals 3 to the power -1. Okay, so I can rewrite my logarithms as exponential functions. So our first objective is to change exponential statements to logarithmic statements and logarithmic statements to exponential statements. The definition of a logarithm can be used to convert from exponential form to logarithmic form and vice versa. So in these first 3 examples for this objective, we're going to change each exponential statement to an equivalent statement involving a logarithm. Okay. So for the first one, a, 1.6 to the third equals w. So the common thing between exponential and logarithmic statements is that your base is going to be the same. And then your equal value and your power switch places. So this exponential statement as a logarithm will be 3 equals the log base 1.6 of w. All right, for b, e to the power u equals 25. So u, not 25, so equals aren't the same. So u equals the log base e of 25. And c, b to the 5th equals 27. So 5 equals the log base b of 27. Alrighty. So now let's convert from logarithmic statements to exponential statements. So we're going to change each of these logarithmic statements to an equivalent statement involving an exponent. Remember, the base is the same in logarithmic and exponential statements. It's the equal value and the power that switch. So log base b of 8 equals 3 is equivalent to b to the third power equals 8. Log base 3 of c equals negative 2, so 3 to the power negative 2 equals c. And c, log base 4 of 6 equals w, so 4 to the power w equals 6. All right. Objective 2, evaluate logarithmic expressions. So to find the exact value of a logarithm, we write the logarithm in exponential notation using the fact that y equals log base a of x is equivalent to a to the power y equals x, and use the fact that if a to the power u equals a to the power v, then u equals v. Okay. So for this next example, we want to find the exact value of each logarithmic expression. So for a, we have log base 3 of 81. So we're going to set this expression to y. So y equals log base 3 of 81. Now that it's in equation or statement, we can now rewrite this logarithmic statement as an exponential statement. So we'll now have 3y, 3 to the power y, equals 81. Now we have 3 to the power y on the left-hand side and 81 on the right-hand side. So to solve for y, we want to make the same base on both sides. Right now we have 3 on one side and 81 on the other. Can I make one of these bases look like the other? And I sure can. 81. So I'll have 3y equals 3 to the fourth, because 81 can be written as 3 to the fourth power. So now that I have the same base, I can drop my bases and set my exponents equal to each other, and I get y equals 4. Therefore, the log base 3 of 81 is going to equal 4. Okay, let's solve b. So I have the log base 5 of 1 over 125. So we're going to set this expression equal to y. That's the first step that we're going to do. Then we're going to rewrite this logarithmic statement as an exponential statement. So that will be base 5 to the power y equals 1 over 125. Now I want to get the same base on both sides. So one side I want to rewrite it with a base of 5. So I know 5 to the power y is going to equal 125 to the negative 1 power, because that's the negative exponent. Now I know 125 is equal to 5 to the third power. So 5y equals 5 to the third power, where our power 3 is going to be multiplied by negative 1, because all I did was rewrite the 125. Okay, so when I simplify this, I get 5y equals 5 to the negative 3. So now that I have the same base, I can drop my base and set my powers equal to each other. So y equals negative 3. Therefore, the log base 5 of 1 over 125 equals -3. Awesome. All right, objective 3. Determine the domain of a logarithmic function. So the logarithmic function y equals log base a of x has been defined as the inverse of the exponential function y equals a to the power x. That is, if f of x equals a to the power x, and the inverse of f of x equals log base a of x, recall from the discussion of inverse functions that the domain of our inverse function is going to equal the range of the original function, and the range of the inverse function is going to equal the domain of the original function. Therefore, it follows that the domain of the logarithmic function is going to equal the range of the exponential function, which we know to be 0 to infinity. And the range of the logarithmic function is going to equal the domain of the exponential function, which we know to be from -infinity to infinity. Okay. All right. So the next part here summarizes some properties of the logarithmic function. So the properties of our logarithmic function are y equals log base a of x if and only if x equals a to the power y, where our domain is going to be all x values between 0 and infinity, and our range is going to be all values between -infinity and infinity. Okay? So the domain of a logarithmic function consists of the positive real numbers. So the argument of a logarithmic function must be greater than 0. Okay, so that's a requirement for all logarithmic functions. Well, the domain. So for these 3 problems, we're asked to find the domain of each logarithmic function. So for A, our function is f of x equals log base 7 of x minus 5. Now, the domain of a logarithmic function consists of the positive real numbers, which means that our value must be greater than 0. So we're going to take x minus 5 and set it greater than 0. Okay. So in this case, if we add 5 to both sides to get x by itself, x must be greater than 5. So our domain is going to be 5 to infinity. Okay. For B, g of x equals log base 6 of 2 minus x divided by 2 plus x. So 2 minus x divided by 2 plus x, we know, since it's part of a logarithmic statement, must be greater than 0. Okay? So that means 2 minus x must be greater than 0, and 2 plus x must be greater than 0. Why do they both have to be greater than 0? Because, well, if I set my denominator to any value 0 or below, if it's 0, my value will be undefined, so we need that value. And if any value is less than 0, then there's a chance that my denominator will be negative, and we know that this value must be greater than 0. So we want any value that will make 2 plus x greater than 0. Now 2 minus x also has to be greater than 0, because if it's negative, then our value will be negative. And we know that our value for this rational expression must be greater than 0. So we'll solve for x. So we'll have negative x is greater than negative 2. And so x is going to be less than 2 because I'll have to divide both sides by a negative value. And when dealing with inequalities, if I ever multiply or divide by a negative value, then I have to switch my sign. And over here, I'll have x is greater than negative 2. Okay, so my domain is going to be from negative 2 to 2. All right. In our last example, h of x equals log base 1/4 absolute value of x. Okay, so our absolute value of x must be greater than 0. Okay, note that x cannot equal 0. All right, because then that would make this inequality untrue. Okay, so our domain is going to be from negative infinity to 0, union 0 to infinity. Okay, because whether we substitute in negative values or positive values, we'll always get a positive value, but we know that this value cannot equal 0 because our logarithmic has a domain that consists of all positive real numbers only. All right, objective 4. We're now going to go into graphing logarithmic functions. So recall that exponential functions and logarithmic functions are inverses of each other. Because of this, the graph of the logarithmic function y equals log base a of x is the reflection about the line y equals x of the graph of the exponential function y equals a to the power x. Okay, so we have here our exponential function y equals a to the power x and our logarithmic function, which is the inverse of that. Okay, alrighty. And then over here we have the same thing, very similar, except this is for when RA is greater than 1. So it looks a little different. This is where A is between 0 and 1. Okay, so it's less than 1. Greater than 0, and B is greater than 1. But just note that when we have our exponential function with the base within these requirements, we get the inverse function, which is our log function, reflected over the line y equals x. So looking at some properties of the logarithmic function, okay, the domain is the set of all real numbers or 0 to infinity using interval notation. The range is the set of all real numbers or negative infinity to infinity using interval notation. The x-intercept of the graph is 1, and there is no y-intercept. So if we go back to our image, we can see here that it intercepts the graph, all right, at x equals, those are y-intercepts. That's on the exponential function. We're talking about the log. So right here, our x-intercepts. All right, so it intercepts the graph at 1, and there is no y-intercept. So note, both log functions do not cross the y-axis. So the y-axis, x equals 0, is a vertical asymptote of the graph. A logarithmic function is decreasing if a is between 0 and 1, and is increasing if a is greater than 1. Okay, so again, looking at our graph, We see here that if a is between 0 and 1 in our first image, our value is decreasing, our graph is decreasing. Whereas if a is greater than 1, you can see here that our y values are increasing. Okay. The graph of f contains the points 1, 0, a 1, and 1/2 a negative 1. The graph is smooth and continuous with no corners or gaps. Okay. So if the base of a logarithmic function is the number e, the result is the natural logarithmic function. This function occurs so frequently in applications that it is given a special symbol ln. That is y equals the natural log x if and only if x equals e to the power y. So recall e is approximately 2.72 rounded to 2 decimal places, but we'll use a calculator when obtaining decimal approximations when working with e and write the exact value using the letter e. Okay. Since y equals the natural log x is the inverse of y equals e to the power x, we can reflect the graph of y equals e to the power x about the line y equals x to obtain the graph of the natural log function. So similar to how we observed the log function, the natural log function is going to be the inverse of e to the power x. So if we have the graph of e to the power x, then we can reflect it about the line y equals x to find its inverse function, the natural log of x. Okay. So we're now going to find the domain of the logarithmic function f of x equals negative natural log x plus 1. So similar to the logarithmic function, the natural log also has to have a domain that's greater than 0. So we're going to take x plus 1, set it to greater than 0, solve for x, so x must be greater than negative 1. So our domain is going to be from negative 1 to infinity. Okay. So now we are going to graph f of x. And we're first going to start off with our base, which is the natural log function. And then we're going to apply transformations to help us get our function f of x. Okay. All right. So first, we start off with our function y equals the natural log x. Our first transformation is we are going to multiply each y by negative 1. So we're going to then reflect about the x-axis. Okay. So this is going to give us y equals negative the natural log x. Okay. So when I reflect it about the x-axis, I now have 1 divided by e1. So that's going to be approximately here. And then let's label that 1 over e1. And then I have my next point, 1, 0, which stays 1, 0. Then my next point, E1, is now going to be E negative 1. So E negative 1. Okay. Alrighty. So so now it's going to be looking like this. Okay. All right. Next transformation, we are going to replace x with x plus 1. So this means that we're going to shift left 1 unit. Okay. So now 1, 0 becomes 0, 0. And e negative 1 becomes e minus 1 minus 1. So that will be e minus 1 minus 1. And then 1 over e1 now becomes 1 over e minus 1, 1. Okay. And so our vertical asymptote, which was the y-axis, also shifts. So we're now approaching our vertical asymptote at x equals negative 1. And so this will be our point. Let's label that 1 over e minus 1, 1. And then we can connect our dots. Alrighty. So from the graph, we can now determine the range and vertical asymptote of f. So looking at our graph here, which is now the graph y equals the negative natural log of x plus 1, okay, our range is going to be all real numbers. So it's going to be from negative infinity to infinity. Our vertical asymptote is going to be x equals negative 1 because it shifted to the left 1 when we replaced x by x plus 1. So now we can find the inverse of f. So to do that, we're going to take our function f of x. We're going to switch f of x to y. So y equals the natural log of x plus 1. Okay. Now, when we are trying to find our inverse function, we interchange our x and our y. So x equals the natural log of y plus 1. Okay, so now after interchanging, we now want to solve for y. So first I'm going to divide both sides by negative 1 because I want to get y by itself. Then I'm going to rewrite this natural log statement as an exponential statement. Note that the base of the natural log is e. So I'll have e to the negative x equals y plus 1. So then y equals e to the power negative x minus 1. So our inverse function of f of x equals e to the power negative x minus 1. Okay. So next, we're going to identify the domain and range of this inverse function. So knowing what the domain and range of f of x will allow us to find the domain and range of the inverse of f, because it's just the reciprocal, the opposite. So since the range of f of x was negative infinity to infinity, the domain is going to be from negative infinity to infinity. The range is going to be the domain, which is negative 1 to infinity. Okay. All right. Now let's graph the inverse function of f. Okay. So first let's graph our function f of x. So we had our vertical asymptote here. Then we had 1 over e minus 1, 1. So that's approximately here. Then we had 0, 0. And we had e minus 1, negative 1, which is right here. So this was our original function, f of x. Now we want the inverse function of f, and that's going to be reflected over this line, y equals x. Okay. So now we are going to be approaching the line y equals negative 1. Okay. Now our point 1 divided by e minus 1, 1 is now going to be negative 1, 1 divided by e minus 1. Okay, so that's going to be right here and right here. Okay, then we're going to have, well, actually, that was a positive one. So we had 1 divided by e minus 1, 1. So we'll have 1. Let me erase that. That's in the wrong spot because it wasn't negative. There we go. So we'll have 1, and then we'll have 1 divided by e minus 1, which would bring us down here. There we go. And then we had 0, 0, which is still 0, 0. And then we had e, so this point right here, e minus 1, negative 1. So then we'll have negative 1, and then e minus 1, which would be approximately right here. So I got those two mixed up. Okay. All right. So now let's connect our dots. And we're approaching. All right. And so that is the inverse function of f. Awesome. So if the base of a logarithmic function is 10, the result is the common logarithm function. If the base a of the logarithmic function is not indicated, it is understood to be 10. That is y equals log x if and only if x equals 10 to the power y. Since y equals log x is the inverse of y equals 10 to the power x, we can reflect the graph of y equals 10 to the power x about the line y equals x to obtain the graph of the common log function. Okay, so thus far we've looked at logarithmic functions in general, and then we are now going to look at the second special log function called the common log. The one that we just did was called the natural log. Okay. So here we're asked to graph this function f of x equals 2 times the log of x minus 3. First, let's find the domain. So just like all log functions, our domain must be positive real numbers, which means that x minus 3 must be greater than 0. So in solving for x, x must be greater than 3. So our domain is going to be from 3 to infinity. Okay. So now that we know our domain is going to be from 3 to infinity, we can now graph, we can now graph f. So first we're going to start off with our base function, y equals log x. And we're now going to replace x by x minus 3, which means we are going to shift right 3 units. So for this log function, our vertical asymptote was our y-axis, x equals 0. And so since we're shifting to the right 3 units, our new vertical asymptote is going to be x equals 3. Okay? And so that means all of our x coordinates are going to move to the right 3. Okay? So now our point 1 divided by 10 is going to be 3 and 1/10, or 3.1. So 3.1 and then negative 1. Okay. Next we had, excuse me, we have 1, 0. And so now shifting to the right 3 units, we'll have 4, 0. Then we had 10, 1. So now we'll have 13, 1. Okay. And so now we can connect those dots. Okay. And our next transformation. Okay, so this is y equals the log of x minus 3. So next we are going to have to multiply each y by 2. So this is going to stretch vertically by a factor of 2. Okay, so this would give us y equals 2 log of x minus 3. Okay, so since we're going to have a stretch vertically, our vertical asymptote is still going to be x equals 3. Okay, so now our point 3.1 negative 1 is now going to be 3.1 negative 2. Our point 4, 0 stretched vertically is going to be 4, 0, so that doesn't change. And then our point 13, 1 is now going to be 13, 2. Okay. So that is our graph for the function 2 log of x minus 3. Okay. So from the graph, we can now determine the range. So if we look here, our range is going to be all real numbers. So that's going to be from negative infinity to infinity. And our vertical asymptote is x equals 3. So if we want to find the inverse function, we first will set our original function f of x to y. So that's 2 log of x minus 3. Once we set it equal to y, we can interchange the x and the y in our function. After interchanging, we now want to solve for y. So we'll first divide both sides by 2 in order to get the log all by itself. Then we will write this log statement as an exponential statement. Since we're dealing with a log and no visible base, we know that the base is the common log 10. So we'll have 10 to the power x divided by 2 equals y minus 3. So in adding 3 to both sides, we get y by itself, leaving us with 10 to the power x divided by 2 plus 3. So our inverse function is going to be 10 to the power x divided by 2 plus 3. Okay. So we can now state the domain and range of our inverse function. The domain of our inverse function is going to be the range of our original function, which is negative infinity to infinity. Our range is going to be the domain of our original function, which is 3 to infinity. Okay. So we can now graph the inverse function. So first let's graph our original function f of x. So we had our vertical asymptote at x equals 3. And then we had our points, 3.1, negative 2. And then we had 0.40. And we had our 0.13, 2. Okay, so I'm going to connect those dots. Okay. And we know this is going to be reflected about the line y equals x. Okay. So now we are going to have the point 2, 13. Oh, that's going to be way up here somewhere. And then we have the point 0.04. And then we have the point 2, 3 point, well, this was a negative 2 actually. So negative 2, 3.1. So this will be like right here and then 3.1. Okay. And we now also have a horizontal asymptote at y equals 3. So our graph looks something like that. And that is the inverse of f. All right. And we have them both graphed. Yay! All right, objective 5. So equations that contain logarithms are called logarithmic equations. In the expression log base a of m, remember that a and m are positive and a does not equal 1. So when solving logarithmic equations, be sure to check your apparent solutions in the original equation and discard any that are extraneous. So some logarithmic equations can be solved by changing the logarithmic equation to an exponential form. So using the fact that y equals log base a of x means that a to the power y equals x. Okay. So here are some steps for solving basic logarithmic equations. So when solving logarithmic equations involving a single logarithm containing the variable, try the following. The first is to isolate the logarithm. That means you don't want anything being multiplied by it, added to it, subtracted, being divided by it. You just want the log with its base and its x. Then you want to change the logarithmic form to an exponential form and solve the resulting equation. So let's do these two examples together. For a, we have log base 2 of 3x minus 2 equals 4. First thing we want to do is isolate our log, meaning we don't want anything attached to it by multiplication, division, addition, or subtraction. We see here that for both a and b, both of our logs are already isolated. So we're good to go on step number 1. So now for step 2, we want to change our log form to an exponential form. Okay, so log base 2 of 3x minus 2 equals 4, written as an exponential statement, will be 3x minus 2 equals 2 to the 4th. Okay. Simplifying, 3x minus 2, 2 to the 4th is 16. Solving for x, I'll get 3x equals 18 by adding 2 to both sides. Dividing by 3, I get x equals 6. Okay. Now I can check this by substituting in 6 into my original log. So the log base 2 of 3 times 6 minus 2 equals 4. So that's the log base 2 of 18 minus 2 equals 4. Log base 2 of 16 equals 4. So 2 to the 4th equals 16. That's true. Excellent. B, log base x of 81 equals 4. So we'll start off with our log. We'll rewrite it as an exponential statement. So that's x to the 4th equals 81. Okay. So to solve for x, we'll take the 4th root of both sides. Okay. So x equals plus or minus 3. Okay. But remember, the base of a logarithm must be positive. Okay. We can't have a negative base. Therefore, x equals only 3. Can't be negative. So when we substitute in 3 for x, we get the log base 3 of 81 equals 4. And 3 to the 4th equals 81 is true. So we know x equals 3 is the correct answer. Okay. So sometimes changing the form from exponential to logarithmic can also be helpful. So we originally did log to exponent to find x, and so now we're going to go from exponent to log in order to help us find x. Okay. So we have e to the power 3x equals 7. So we know if we have a base e, we're working with our natural log, so we can rewrite this as the natural log of 7 equals 3x. Okay. So in solving for x, we divide both sides by 3. So x will equal the natural log of 7 divided by 3. If we were to enter that into our calculator, round to 3 decimal places, we'll get approximately 0.649. Okay, but x will equal the natural log 7 divided by 3. Alrighty. Okay, our word problem, focusing on alcohol and driving. So blood alcohol concentration, BAC, is a measure of the amount of alcohol in a person's bloodstream. A BAC of 0.04% means that a person has 4 parts alcohol per 10,000 parts blood in the body. Relative risk is defined as the likelihood of one event occurring divided by the likelihood of a second event occurring. For example, if an individual with a BAC of 0.02% is 1.4 times as likely to have a car accident as an individual who has not been drinking, the relative risk of an accident with a BAC of 0.02% is 1.4. Recent medical research suggests that the relative risk R of having an accident while driving a car can be modeled by an equation of the form R equals E to the power K times X, where X is the percent concentration of alcohol in the blood and K is a constant. So X is the percent concentration of alcohol, K is a constant, and R is the relative risk. So we know what all the variables are in our function. So A, research indicates that the relative risk of a person having an accident with a BAC of 0.02% is 1.4. Find the constant K in the equation. So let's identify what we know. Well, we know our percent concentration, which is X, and that is 0.02 because it's a percent concentration. We know R is our relative risk, and that is 1.4. And we are asked to find K. So using our equation, R equals E to the power K times X, we can substitute in our values. Why does I put 1 point? There shouldn't be a 1 there. There we go. 1.4. Then we have e to the power k times 0.02. Okay. So to find k, we can rewrite this as a logarithmic statement. So we'll have 0.02k equals the natural log of 1.4. Okay. So solving for k, we'll divide both sides by 0.02 and then enter that in our calculator. And let's do that together. Alrighty, so we'll take our equal fraction first, and then we'll enter in the natural log, which is the button here to the left of 4. So natural log of 1.4, close the parentheses, divide by 0.02, and we get 16.82. So let's write that down. 16.82. Okay, so that is our constant. All right. B. Using this value of k, what is the relative risk if the BAC is 0.23%? So they want us to use that same value of k, which is 16.82. They said that X here, which is the percent concentration, is 0.23, and they want to know relative risk, which is R. So entering that into our equation, R equals e to the power k times x, we are going to take e to the power 16.82 times 0.23. Okay, and we are going to find R. So let's grab our calculator. Okay, and I'm going to move this over here. And I'm going to always show it. Okay, so we'll have e to the power. So I'm going to take this right here. And then 16.82 times 0.23. Enter. Okay, and I get R equals 47.88. We'll round to 2 decimal places. Okay, so this means a person with a BAC of 0.23% is 47.88 times as likely to have a car accident as a person with no alcohol in the bloodstream. Okay. All right, let's now do C. So using this same value of K, what BAC corresponds to a relative risk of 85. So we're using the same K, so that's 16.82. And we are trying to find the X, which is the percent concentration of alcohol. So our R here is 85, and we want to find X. So using our equation, R to the power kx, we'll have 85 equals E to the power 16.82x. So to find x, we're going to have to convert this exponential statement to a log statement. So we'll have 16.82x equals the natural log of 85. So x will equal the natural log of 85 divided by 16.82. So we'll enter that into our calculator to get the approximate value of x. So we'll have our fraction, then the natural log of 85 divided by 16.82, and x is approximately 0.26. Okay, so that means for a blood concentration of 0.2%, 0.26 or 26%, the relative risk is 85. All right. So if the law asserts that anyone with a relative risk of 4 or more should not have driving privilege, at what concentration of alcohol in the bloodstream should a driver be arrested and charged with a DUI? So driving under the influence. Okay. So here our relative risk is 4. Our K is 16.82. And we're trying to find x. Okay. So our function is r equals e to the power kx. R here is 4, and k is 16.82. So rewriting this as a log, we'll have 16.82x equals the natural log of 4. So x equals the natural log of 4 divided by 16.82. So then x is approximately a value that we'll use our calculator to help us find. So we'll take alpha and then natural log 4 divided by 16.82, enter, and we will get 0.08 to 2 decimal places. So this means that a driver with a BAC of 0.08% or more should be arrested and charged with the DUI. Okay, so note that in most states, actually, the blood alcohol content at which a DUI citation is given is 0.08%. So this is very relevant to our real world today. All right. All right, so that concludes section 4.4.